Good afternoon, student. Yesterday we have discussed the example how to obtain the transfer function for the given block diagram. Okay, so here we can see that here in forward path there are two blocks are there, G1, G2, and there is a one summing point, and that there is output. One block is there in parallel with the G2, and therefore we can reduce this block by one block, because these two blocks G2 and G3 they are in parallel, and therefore blocks G2 and G4, G2 and G3 they are in parallel. Okay. This block G2 and G3 they are in parallel, therefore we can they can be combined into the single block with a gain of when they are in parallel. So this is G2 and this is a minus sign, therefore G2 minus G3. So G2 minus G3, and therefore we can reduce that whole summing point and two blocks by only one block having the gain G2 minus G3. Now these two blocks are in cascade. When these two blocks are in cascade, we can represent these two blocks in one block, and the gain of that block will be the product of that individual blocks. Okay, so this is a G1 into G2 minus G3. They are in cascade, and therefore we have written like this. Our block diagram will be reduced to like this: G1 into G2 minus G3. Therefore, we have to just the product of the individual block, and we have to reduce it by the one block. Next, what we can do here now, see, we cannot do anything here because this summing point is in between these two blocks. So either you move this summing point after this ahead of this block, or we move after this block. So we'll move a summing point after this block, H2 block. So in moving this summing point after this block, these two blocks will come near to each other, and this block will be on the left side of this H2. But in doing so, this will also create one more blocks in the feedback path. This will create one more blocks in the feedback path, and therefore the block diagram will be reduced like this. So I have taken the feedback path ahead of this block H2. So H2 will come on the right side of this summing point, and again there will be one more block is created in feedback, and the gain is H2. And now H2 and H1 they are in cascade, G4 and H2 they are in cascades. So we can represent it by one block, and we can also represent it by one block. The gain of this one block will be H1 H2, gain of this block will be H2 G4. So in the next diagram I have shown this. Okay, I have taken the product of this individual gain. Okay, now we have to interchange the summing point. See, this feedback is coming here, it is going here, this is negative sign, and again it is negative sign. So negative will plus, and therefore we can interchange the summing point like this. We can separate this feedback path by this line, and therefore now we also separate like this. So now we have this one feedback loop, and this is two parallel paths are there. This path of this gain of this path is suppose 1. So we can write here 1 plus G4 H2. So we have written here 1 plus G4 H2, and this block we can represent like this. We have to remove this feedback loop. So what is the G here? This is the value of G. So G 1 plus GH. So this is value of G, and this is value of H. So I have written like this, and I have reduced this whole feedback loop by only one block having the transfer function like this. So this is the value of G, and this is the value of H. So I have written here G upon 1 plus GH. So this value I have written here. So now there are two blocks are there, they are in cascade. Again we can multiply this, and we can find the transfer function, that is the output by input. So C by R, and I have found that C by R this into this. Okay. Similarly, I have next I have solved this G1, G2, G1, G3, and again I have solved this with these brackets. I have solved this with this bracket, and finally I have got this transfer function. So this is the transfer function by the given block diagram by using the block diagram reduction rules. So this is yesterday's examples. Okay. Now we will move towards next, that is a signal flow graph. So the block diagram we have seen, it is useful for the graphically representing the control system. So whenever we have to represent the control system, we can graphically represent it by the block diagram. And block diagram is used in the analysis and design of the control system. But what is the alternative to the block diagram? It is the signal flow graph. An alternative approach to the graphically representing control system dynamics is the signal flow graph approach, and this is developed by the S.J. Mason. This signal flow graph is developed by the S.J. Mason, and it is noted that the signal flow graph approach and the block diagram approach, it gives the same information. It is not like that the block diagram, if you use the block diagram or if you use the signal flow graph, both will give the same output. Okay, both will give the same output. But whenever the block diagrams are very complicated, it becomes tedious to use those block diagram reduction rules, and therefore it is very necessary to go for the signal flow graph, and we have to use the formula which was developed by the S.J. Mason. So what is the signal flow graph? So signal flow graph is a diagram that represents a set of simultaneous linear algebraic equation. Okay, when applying the signal flow graph method to analyze the control system, we first transfer the linear differential equation into the algebraic equation with the help of the Laplace transform. So signal flow graph consists of the network in which the nodes are interconnected by directed branch. Each node represents the system variable, and each branch connected between the two nodes act as a signal multiplier, and the signal flows in only one direction. The direction of the signal flow is indicated by the arrow placed on the branch, and the multiplication factor is indicated along the branch. So I will just draw one signal flow graph so that we will get the idea. The signal flow graph is like this. So this is a node x1, this is node x2, this is node x3, this is also node x3. And what is the transmittance is here 1, transmittance is here B, transmittance is here A, and one more, it is given like this. What is the transmittance of this? It is a D, and this is x4 node. Okay, so these two nodes we can call it as a mixed nodes. Hello, these two nodes are mixed nodes, and therefore the signal flow graphs contains essentially the same information as the block diagram. Okay, therefore the signal flow graph. हेलो सर, मैं अभी क्लास ले रहा हूँ सर, बोलिए ना क्या. हाँ बोलिए ना सर. हाँ ठीक है भेज दीजिए सर। ओके ओके ठीक है। So this signal flow graphs I have shown like this. So this is the what we can say it is a node. We will define some definition to this related to this signal flow graph. What is node? Node is a point representing a variable or signal. So this node is a point representing variable or signal. Next is the transmittance. So transmittance is a real gain or a complex gain. Transmittance is a real or complex gain. Between the two nodes. Now see the these are the two nodes, that is x1 and x2, x1 and x2, and therefore A is the transmittance. A is the transmittance, that is between the two nodes. Okay. Next is the branch. What is the branch? Branch is a directed line segment joining two nodes. This is the branch. Branch is a directed line segment joining the two nodes. That is called as the branch. Okay. And the gain of the branch is a transmittance. So this is the branch. And what is the gain of this branch? It is the transmittance. That is A. A is the gain of this branch, x1, x2. Next is the input node. Or it is also called as the source node. Input node, or it is also called as the source node. So the input node or source node is that node which has only outgoing branches. So we can call this as the input node. X1 is the input node because it has only outgoing branches. And there is no incoming branch to this node X1. So this node we can call it as an input node, or we can call it as a source node. Similarly, we can call at the second is the output node or sink node. So X3 we can call it as an output node, or we can also call it as a sink node. Okay, output node or sink node. So the output or sink node, it is a node that has only incoming branch. So it has only incoming branch, and it has not having any outgoing branch. So that is why it is called as the output node, and it is also called as the sink node. So this is x1 is the input node because it has only outgoing branch. Similarly, this is also x4 is also input node. X4 is also input node because it is having the output branch. It is not having any incoming branch. So this is also the example of the input node. Next is the mixed node. Mixed node, it is a node that has both incoming and outgoing branches. So these are the mixed nodes. X2, X3, these are the mixed node because it is having incoming branch as well as outgoing branch. So X3, it is also mixed node because it is having the incoming branch as well as outgoing branch. So this X2 and X3, we can call it as a mixed node, as it has both incoming and outgoing branches. Next is the path. So path is a traversal of the connected branches in the direction of branch arrow. So this is, we can call it as a path. This is one path. This is another path we can call. So this path is a traversal of the connected branches. So these are the connected branches in the direction of branch arrows. So this is the direction of branch arrows. So the path is from x1 to x3. Okay. And if no node is crossed more than once, then path is open. If no node is crossed more than once, then the path, we can say it is a open path. Okay. If the path ends at the same node from which it begins and does not cross any other node than once, it is closed path. Okay. Next is the loop. Loop is a closed path. What is loop? Loop is a closed path. So I will show here one loop. So this is the one loop. So the loop is this starting from this x2. This is going in this way. Again, the signal is coming at x2. So we can call it as a closed path. We can call it as a closed path, and this is called as the loop. So, and the next is the loop gain. What is the loop gain? It is a BC. What is the loop gain of this? It is a BC. Okay. So I will write here loop gain means the product of the these two branches, because these two branches are in this loop. So what is the loop gain? It is a BC. Okay. So the loop gain is the product of branch transmittance of a loop. Okay. Next is the non-touching loops. Non-touching loops. So there are some loops which may not touch. Suppose there are these loops. There is one, suppose one loop. I will show here. This is suppose x4 point, x4 node. Okay, and I will show here suppose such type of the loop. So this is one loop and this is one loop. So these two loops are non-touching loops because these two loops are not touching to each other. If suppose the loop is here, then that loop will be touching loops. This and this loop will be touching loop. But the loop is here, another loop is here. Therefore, there is no touching to each other, and therefore we can call it as a loop or non-touching if they do not possesses any common nodes. Okay, this is possessing any. This is actually this is possessing common nodes. So we will give this name to this like this. Suppose this is x4, this is x5. Okay, so now these two loops, they doesn't containing any common loops. So I will give this name to this. Suppose this is the transmittance of this branch, suppose E. Okay, so now these two nodes, they doesn't have any common nodes. Next is the forward path. Not non-touching loops. Next is the forward path. Forward path means once the path, forward path is a path from input node to an output node. So this is the input node and this is the your output node. So this is a forward path. This is the one forward path. Second forward path is this. This is also input node. So this is our second forward path. Okay. So forward path gain. Again, what is the forward? There are two forward paths. The gain of the first forward path is A, B, E. And the gain of the second forward path is D, E. So this is the forward path gain. So in this way, we can, these are some definition related to the signal flow graphs. Now, there are some properties of the signal flow graph, important properties of the signal flow graphs. Properties of signal flow graph. So the branch indicates the functional dependence of one signal on another. Okay, this is the first property. Now this branch is dependent on this signal x1 as well as this transmittance A, because whatever the signal is coming from this coming to this node, it is get multiplied to this transmittance B. So the branch indicate the functional dependence of one signal on another. A node adds the signal of all incoming branches and transmit this sum to all the outgoing branches. So this node, this will add all the signal coming to this node, and this will transmit all the signal which has come at this node to the other nodes. So this is the property of the signal flow graph. At the same time, a mixed node which has both the incoming branch as well as the outgoing branch. This is the mixed node x2 and x3. So the mixed node which has both the incoming and outgoing branch may be treated as an output node by adding an outgoing branch of unity transmittance like this. So these are for a given signal, for a given system, the signal flow graph is not unique. Many different signal flow graph can be drawn for a given system by writing the system equation differently. So whatever the signal flow graph will get, and that is not a unit, we can draw the many signal flow graphs for the given system by using the different system equations. Okay. So the next is the signal flow graph algebra. Signal flow graph algebra. So signal flow graph of a linear system can be drawn using the what you have seen just now according to the definitions. In doing so, we will bring the input node to the left and output node to the right. Independent and dependent variables of the equation become input node and output node respectively. The branch transmittance can be obtained from the coefficient and equation, and therefore to determine the input output relationships we have to use the Mason's gain formula, which will give, we will discuss that Mason gain formula. So we may deduce the signal flow graph to the graph containing only one input and output nodes. So for example, this is suppose x1 x2, and this is the transmittance is A. Okay, transmittance is A. Therefore the value of node with only one incoming branch, it is shown. So what is the, we can write x2 is equal to A into x1. So this is the value of a node with only one incoming branch. The total transmittance of the cascaded branch is equal to the product of all branches of all branch transmittance. The cascaded branch can combine into the single branch by multiplying the transmittance. For example, like this, the total, so this is the node x1, this is node x2, this is node x3, and transmittance is A, here transmittance is B, and therefore we can draw here the, we can write here x1 x3, and the transmittance is there AB. Transmittance is there AB. In this way we can take the product of the individual transmittance. So the total transmittance of series branches is equal to the product of all branch admittances. Parallel branches may be combined by adding the transmittance. If there are two parallel branches are there, there are two parallel branches, are suppose this is x1 node, this is x2 node, and this is the one path having the transmittance A, this is another path having the transmittance B, and therefore there is a parallel path between these two nodes, and therefore this can be represented by only one branch with node x1 and x2 by the addition of this transmittance of the individual branch. Okay, so this is हो बैठो उधर बैठो मैडम के पास थोड़ी देर so these two, there are two parallel paths, path A and path B, and therefore the we can represent such we can take the addition of this individual transmittance A plus transmittance B, and therefore we can add like this. Next is the a mixed node may be eliminated. If there are some mixed nodes are there, mixed node may be eliminated. And mixed node, how to eliminate the mixed node? Suppose like this. The mixed node, here it is x1, this is x2, x3, and this is x4. How to eliminate the mixed node? And the transmittance of this node of this branches are A, B, and this is C. So how to eliminate these nodes? That we can write like this. This is x1 to x4. This is x2 to x4. So here it is AC and here it is DC. So in this way we can reduce the mixed node. We can reduce the mixed node, or we can eliminate the mixed node. So loop may be eliminated. If there are again some loops are there, that loops may be eliminated. For example, loops like this. If there is only one loops, suppose this node x1 is there and this is x2 node. This is the transmittance of this path is A, this is B, and this is C. Okay, this is node x1, x2, and this is x3. So how to reduce this loop? This loop can be reduced by so this is, we can say it is A, B, this is node x1, this is x3, and therefore this is BC. Okay, we can reduce this loop like this, and finally we can also write this x1 to x3, that is AB upon 1 minus BC. So in this way we can reduce this loop. And finally we can write here x3 is equal to AB x1 plus BC x3, and or we can write here x3 is equal to AB upon 1 minus BC into x1. So this is how we can use these different properties, or this is the signal flow graph algebra for drawing the signal flow graphs of any systems. So what is the signal flow graph? We have to draw the signal flow graph because whenever the system is given to you, so the system is represented by the simultaneous equations. Okay, so therefore the simultaneous equation can be represented by the signal flow graph, and the signal flow graph that represent the set of simultaneous linear algebraic equations. And now we have to apply the signal flow graph methods, and we must first transfer the linear differential equation into the algebraic equation first. So let us consider one system having the following set of equations, and we have to draw the signal flow graph for that. Okay, so one by one we'll draw this. Let us consider the following set of the equations. The equations are given: x1 is equal to a11 x1 plus a12 x2 plus a13 x3 plus b1 u1. Similarly, x2 is equal to a21 x1 plus a22 x2 plus a23 x3 plus b2 u2. This is second equation is given, and the third equation is x3 is equal to a31 x1 plus a32 x2 plus a33 x3. Now see, in this case here u1 u2 are input variables in this equation. Here u1 and u2, these are the input variables, and x1 x2 x3 are the output variables. x1 x2 and x3 are the output variables. Now we have to draw the signal flow graph. We have to draw the signal flow graph. So we have to take the advantage of this. So first node is here x1, and to this x1 this input is coming. Okay, so by taking the help of this equation, I can now draw the signal flow graph. So this is x1, this is your u1, this is x2, this is x3. Okay, so these are the variables, and input variables is u1. So okay, so to this x1, one signal is coming starting from x1, and it is also coming at x1. Okay, another is coming from x2, that is a12, and to this x1 another signal is coming, that is a13, and one more signal is coming b1. So for this I can now write the signal flow graph, or I can draw the signal flow graph like this. So x1 is equal to, this is a b u, x1 is equal to b u1, and to this x1 the self loop is there. So this is a x1 is equal to a11 x1. So this is a a11 x1, a11 x1. Now again a12 x2, a12 x2. So the signal which is coming at x1 is a12 x2. Similarly, one more is a13 x3, a13 x3. So it is coming like this, a13 x3. Okay, so in this way we can draw the signal flow graph for the first equation. Similarly, you go for the second equation and third equation. So for the second equation, that means x2, this is x3, so x2, one signal is coming from x1, that is a, and transmittance of that signal is a21. So we can draw like this, a21, the transmittance of that signal is a21. Similarly, one signal is coming from x2 to x2, so that means it is a self loop. A22 is the self loop, so we can A22 is the self loop like this. A22 is the self loop. This is also like this. This direction will be like this. So A22 is the self loop. Okay. This is A22 is the self loop. Now one signal is coming from X3. That is a 2-3. X3. So X3, one signal is coming from to X2. That is A13. Now it is a A23. A23. And one more is that is a B2 U2. One is the B2 and this is input U2. So in this way we can draw the signal flow graph for the second equation, and the third equation is remain. Now X3 is the signal coming to X3 is from X1, X2 and X3. Okay, so the signal coming from X1 is A13. X3, that is a A13. So it is a A13. A13 signal coming from X1. Signal coming from X2, A32. X2, A32. Signal coming from X3 to X3. That means it is a self loop A33. Okay, and we can extend this. We can give the name to this also X3. So this is a self loop. Okay, and we can give the gain of this. It is 1. So this is the signal flow graph for the given set of the equations. This is a signal flow graph for the given set of equation. In this way we can draw the signal flow graph for the given set of equation. So I think this much is sufficient today. Okay, I will share the attendance. Link. Only 16 students. Okay, they should fill this form immediately. Okay.